Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, moving right along, let's move on to the first listener phone call.
Hi, Professor Kaku. I was just wondering, I was recently reading a book by David Eagleman where he spoke about how people can replace one sense, like the sense of hearing, with another, like the sense of touch. And so I was just wondering if you had any ideas or interesting things to talk about how there might be some other things that our brain is just not equipped to perceive out there. Thank you very much.
Well, in fact, I had Dr. Eagleman on Science Fantastic asking him about the very things that you mentioned. There's something called synesthesia. And synesthesia is basically people who get their senses confused. So instead of hearing something, they see light. Now, I actually had somebody with synesthesia on radio. And he suffered from Asperger's syndrome, and he had an incredible memory. He memorized pi, the number, he memorized pi to about 10,000 decimal places. He holds the world's record for memorizing pi, and in fact, he had to have a team of people checking him as he rattled off all the indices of pi. It took him several hours to recite all the digits. So I asked him, how is it possible, Mr. Tennant, that you can memorize pi to 10,000 decimal places? And he says, well, he associates a color with each of the 10,000 digits. You see, he also suffers from synesthesia. When he hears a number in his mind, he sees a color because the wiring of his brain, there's a mismatch. And then I asked him, well, how do you memorize 10,000 colors? And he said, well, I really don't know. It just comes to me, and that's how he memorized pi to 10,000 decimal places. Now, what this means is that your brain also has that same capability. There's several theories that I mentioned in my book about how it's possible the brain can do this, but genetically, we're not all that dissimilar. Therefore, if this guy can do it, has a photographic memory, then it's possible that you too might have a photographic memory, but it's been turned off. So when you interview these people with photographic memory, they sometimes say that they wish they didn't have it because all these totally extraneous, unimportant facts come hitting at them, totally useless. One woman, for example, is a housewife in Los Angeles. She has a photographic memory. If you ask her, what were you doing at 2 o'clock in the afternoon 10 years ago to the very day, she'll tell you what she was doing 10 years ago at 2 o'clock in the afternoon. And she says it's like having split memory. It's like one part of your brain reliving a day 10 years ago, and the other part of your brain seeing everything that you are seeing now. Totally useless, she said. So in other words, maybe nature mercifully gave us the ability to forget. Now, one theory that explains this is that we used to think that forgetting occurred naturally, that with time, memories degrade. There's a new theory out there which kind of shocked me when I heard it. And that theory is that your brain records memories, and then your brain has to deliberately erase memories as well. Erasing is just as complicated as remembering. Erasing doesn't occur naturally at all. Now, if that's true, then these people have a broken erase mechanism. Their brain has forgotten how to erase. Their brain just memorizes everything in sight. If this theory is true, this means that you too may have this ability to remember everything that your senses record. But in these individuals, in fact, in most people, it's been turned off. However, in these people, it's broken, and therefore they memorize everything. And in fact, if you want to know more about this, get a copy of my book, The Future of the Mind. I have a whole chapter on things like this. And let's now take a short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we're throwing the lines open in this hour. So let's take the next listener phone call.
Yes, sir. I was listening to your show. I'm kind of a first-time listener, and it's fascinating. I love science. My question would be, how does a creator, intelligent design, or the beginning of the world, or God, if you will, fit in to science, and how you feel about that?
Well, that's a big question, so let me try to break it down. First of all, Galileo himself, the founder of modern science, was asked that question, and he answered it as follows. He says the purpose of the church is to determine how to get to heaven, and the purpose of science is to determine how the heavens go. So in other words, they're different. The purpose of the church is to determine how to go to heaven. In other words, ethics, behavior, how to act like a good person. That's what the church is all about. And science is about how the heavens go. That is, it's about natural law. It's about the laws of the universe. Now, the problem occurs when scientists begin to pontificate about ethics, or when religious people begin to pontificate about natural law. That's where the problem occurs, because as long as you keep the two distinct, realize that science does not tell you what is a good thing or a bad thing. That's what society tells you. Where do you draw the line between a felony and a misdemeanor? What is good? What is bad? These are things that society has to democratically decide upon. However, in science, we talk about things that occur in natural law throughout the universe. What does a felony or a misdemeanor mean on another star system? So you begin to see that they're two different domains, so they're not necessarily in opposition to each other at all. Now, then Einstein was asked the question, do you believe in God? And he says, well, let's break it down. There are two kinds of God. First, there's the personal God, the God that you pray to, the God that parts the waters. And he said that he did not necessarily believe in a personal God because we're talking about the creator of the universe. Does the creator of the universe really care about killing the Philistines or whether or not you pray to get a bicycle for Christmas? I think perhaps God has more important things to think about. And then Einstein said he believed in the God of Spinoza. That is the God of reason, harmony, the God of order, beauty, simplicity. Because you see, the universe didn't have to be this way. The universe could have been random. It could have been chaotic. It could have been a jumble of random things. But here we are, living in a gorgeous universe with natural laws that could be figured out by human beings. And he thought that, well, that's the God that he believed in. Okay, well, moving right along, let's take the next listener phone call.
Yes, my name is Lou Cooley. I'm calling because I have a question that perplexes me. How can the universe be in nothing? The universe has to be in something, in my thought, and that has to be in something. It's like it's stranger than fiction. It's so big you can't realize it, and the universe is so small you can't realize it. Can you explain that idea that I'm talking about? Thank you.
Well, you asked one of the deepest questions, a question that theologians have asked. For example, some theologians thought that the oceans, no matter how far they seem to be, are sitting upon a turtle. And the whole universe is basically a disk sitting upon a cosmic turtle. Then the question is, well, what is a turtle sitting on? Well, the turtle is sitting upon another turtle. And how many turtles are there? Well, there's an infinite number of turtles going all the way down. And then the question is, well, what supports an infinite number of turtles? St. Thomas Aquinas was asked this question, and he was asked the question, is there a first mover? Well, why do objects move? Objects move because they're pushed by something. But what pushes that? Well, something else had to push that. But then what pushed that? Well, something else had to push that. And then St. Thomas asked St. Thomas Aquinas asked himself the question, well, if there's an infinite number of pushers, what is pushing that? And so you go crazy trying to think about this. Is there an infinite number of layers of existence? Well, science simply says the following. Well, first of all, science itself evolves. Back in the 1920s, for example, astronomers thought that the universe was the Milky Way galaxy. That's it. Period. End of story. If you ask an astronomer back in the 1920s, how big is the universe anyway? They would say, oh, that's easy. The universe is roughly 100,000 light years across. That's the size of the Milky Way from one edge to the other. That's the universe. But then Edwin Hubble comes along and finds out there are other universes out there. Billions of other universes. And so we're back to the turtle question. How many turtles are there? Now, the short answer is we don't really know at the present time. The Hubble Space Telescope can see 100 billion galaxies out there, each galaxy containing 100 billion stars. And so how many stars are out there? Well, the number of stars we can see with a telescope is 100 billion times 100 billion. That's an incredibly large number, but you can actually quantify it in terms of how big the universe, the visible universe, is. And then the question is, what's beyond the visible universe? And again, the short answer is we don't know. However, let me give you two theories. One theory is that the universe perhaps is just infinite. It just goes on forever, endlessly. That is a solution of Einstein's equation. Another solution of Einstein's equation says that the universe is a ball of some sort. It's a four-dimensional ball. And it's a bubble. And what is the bubble doing? It's floating in a larger ocean. An ocean of turtles? No, it's an ocean of hyperspace, 11-dimensional hyperspace. And so one theory, coming from string theory, says that our universe is a bubble. We live on the skin of the bubble. The bubble is expanding. There are other bubbles out there. And the arena that the universe exists in, that floats in, is 11-dimensional hyperspace. Dimensions beyond comprehension. And it's impossible to explain all of string theory in just a few minutes. Get a copy of some of my books, Hyperspace, Parallel Worlds. I have a whole discussion about string theory and what is 11-dimensional hyperspace. Okay, well, moving right along, let's take the next listener phone call.
Hello, Doctor. I'm calling from Clearwater, Florida. Just thinking about black holes. Is it possible that the black holes are the garbage cans of the universe? Thank you.
Well, you're exactly right. Some people think that black holes are the ultimate Roche motel. Everything checks in, but nothing checks out. So that is a plausible theory. However, it's not satisfying because when a star disappears into a black hole, and we see this happening now with our telescopes and sensors, you kind of wonder, well, what happened to the star? Is it just eaten up? Is there a garbage can there? And is there another side to the garbage can? Well, the short answer is we don't know, because even though Einstein's theory predicts the existence of black holes, even though we see these black holes in outer space, we have to use a higher set of equations, because Einstein's equations break down at the center of a black hole. They're useless. Einstein's equations simply say that the gravity at the center of a black hole is infinite. Now, what does that mean? That doesn't help you at all. We physicists don't believe in infinite energy. What it really means is that Einstein's theory has simply broken down. And again, that's where string theory comes in, because string theory goes right through the center of a black hole. Now, is there another universe on the other side of a black hole? That's one theory. Watch the movie Interstellar, starring Matthew McConaughey. And the people consulting for that movie were Caltech physicists, colleagues of mine. And they use the latest in terms of computer projections and computer simulations to simulate exactly what happens when you go through the event horizon of a black hole and head toward the center of a black hole. Now, of course, this is Hollywood. And what do they find at the center of a black hole? A gateway to another universe. That is a solution of Einstein's equations. And again, do we have the technology to go through the black hole? And the answer is no. So how did they get away with it in the movie? I'll answer that question after the commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we explore the cutting edge of science, the very edge of what is known about this great universe of ours. Okay, well, without further ado, I'll get into the phone calls. However, let me then answer the question that was raised previously. And that is, what lies on the other side of a black hole? The short answer is we don't know. Einstein's equations break down at that point. String theory, however, does go through the black hole. One possible solution, I'm not saying it's the only one, one possible solution is that there's a gateway, a wormhole, a dimensional portal connecting that universe to another universe. And then how do you get the energy necessary to drill a hole in space and time? In the movie, they get around that. In the movie, it turns out that our descendants, our future people of the future do have the technology to create a wormhole to go back into the past and meet us. That's how they get around that very clever trick. How do you create a wormhole through time? And the answer is you have to wait for your descendants to create a wormhole so they can visit you in the past. A very clever way that Hollywood has of getting around that problem. Okay, well, moving right along, let's take the next listener phone call.
Yes, Professor. This is Bob in Chicago. Curious. If you were traveling at the speed of light in a ship, or even on a carpet, a magic carpet, would your mass be infinite once you reach the speed of light? Thank you.
Well, you ask a very interesting question, because if you read Einstein's original paper of 1905, he says that as you approach the speed of light, all sorts of bizarre, strange things begin to happen. First of all, time slows down. That freaks people out. But hey, we measure this every day with our satellites now. Einstein was right. The faster you move, the slower time beats. And that's why your GPS system works. That's why your cell phone works, for God's sake. If it wasn't for Einstein, your cell phones wouldn't work. And you get heavier. In fact, if you hit the speed of light, you have infinite mass. So how do you get around that? Well, you get around that very simply. You cannot reach the speed of light. Now, if you could reach the speed of light, which is not possible, your mass would be infinite. And of course, that's silly. Who ever heard of infinite mass? And so it simply means that Einstein's equations have been verified at sublight velocities. And at the speed of light, you have, of course, light beams. And light beams obey a different set of equations. Light beams have zero rest mass. Therefore, they do not have infinite mass at all. Some people ask that question. Well, if light travels at the speed of light, and if your mass is infinite at the speed of light, then how come light does not have infinite mass? And the answer is very simple. Light has zero rest mass. And therefore, it cannot have infinite mass at all. And so when Einstein came out with his theory, of course, he was hit from all sides. A lot of people didn't believe him. In fact, even Adolf Hitler commissioned teams of scientists to try to tear down Einstein's theory. And of course, they all failed, because Einstein's theory has been experimentally verified. And the simplest verification of Einstein's theory is your cell phone. Welcome back to Science Fantastic with Professor Michio Kaku. Give us a call. The lines are open. Let's take the next listener phone call.
Thank you, Professor, for taking my call. This is Charlie Campbell, 102.3 WGOW, Chattanooga, Tennessee. And my question is about the moon. We all know, well, I guess we do, we all know what the moon does for our planet. All right. At one point, you said that, or they said, that something hit the Earth and knocked off a chunk, and that became our moon. All right. Which came first, the moon or the water, the ocean or the moon? Thank you very much.
Well, you ask a very interesting question, and that is, well, if the moon was blown out of the Earth, which seems likely, then which came first, the oceans or the moon? Well, we're not sure about this because, of course, no one was there to photograph what was happening. But we think that the moon was blown out of the Earth roughly 4.1 billion years ago. Now, the Earth itself is 4.5 billion years old. That's the age of the sun, by the way. The sun, the planets, all condensed out of the same cloud roughly 4.5 billion years ago. We know this by dating meteorites, some of the oldest objects in the solar system, and we also know the age of the sun. The sun is a gigantic hydrogen bomb. We know almost everything about hydrogen bombs because the Pentagon has been funding generously physicists for decades. And we can actually gauge the age of the sun because we know the rate at which the sunshine falls on the planet Earth. So as a consequence, we're able to know that the Earth is roughly 4.5 billion years. And then the astronauts brought back moon rock. And looking at the moon rocks, we realize that the rock of the moon is very similar, almost identical to the rock found here on the planet Earth. And by looking at Newton's laws of motion, we can actually run the videotape backwards and rule out or rule in different scenarios of how the moon was created. All these theories coalesce into one theory, showing that the moon was probably blown out roughly 4.1 billion years ago, plus or minus, of course. Now, the oceans, we're not quite sure where the oceans came from. One theory is that comets and asteroids brought most of the water to the planet Earth. But as you can imagine, even if the Earth had a primitive ocean, a very primitive ocean 4.1 billion years ago, and an asteroid the size of Mars were to hit the Earth and blow the moon into space, whatever ocean we had would vaporize. And so the answer to your question is perhaps the moon was born first and the oceans came later. But again, we think it was a process. We think it took millions of years for the oceans to form, and we're still learning more about the solar system. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, moving right along now, let's take the next listener phone call.
Professor Kaku, this is William. My question is there a homosexual gene that a person can inherit even though there is no history of homosexuality? Thank you very much.
Well, you ask a very controversial question, and there's only a limited amount of reproducible, testable, falsifiable data on this question. In fact, I interviewed one of the leading biologists who has tried to find the so-called gay gene. In fact, he announced several years ago that he thought he was hot on the trail of a gay gene, but since then, other researchers have not been able to reproduce his results. Now, we know there is some genetic component to it, but it's not 100%. In other words, there's not just one gay gene. It turns out if you look at identical twins, you can have one twin who is gay and the other one who is not. If it was simply a single gene that determined whether or not you were gay, then of course you wouldn't have that. However, you can look at the genetics and you see that, well, there could be a genetic link. That is, if you are gay, then yeah, there's a slight elevated chance that perhaps your siblings are also gay as well. And so, to summarize, there's no proof one way or the other as to whether or not there is a gay gene. They're just theories. One theory, for example, says that perhaps in the fetus, perhaps the fetus is bathed with hormones which then determine whether or not the brain is going to be male or female. You see, we are born female. We're all born female, But then we have hormones hitting us in the womb, which then determine whether or not we are male or female. So you can be genetically male, but your brain tells you otherwise, depending upon the amount of hormones that you get in the fetus. But again, let me stress again, these are just theories. We have no definitive proof one way or the other, even though people have tried to look for a gay gene. And in fact, I even had one of the leading individuals, Professor Hammer, who claimed to have found a gay gene. So at the present time, it's up in the air. Okay, well, let's go to the next listener phone call.
Yeah, hi. I've always wondered if a plane in space, like in a spaceship, will continue to be a flame, and always wondered if a propeller on one of those rubber bands, if you could wind up a rubber band with a propeller attached to a little airplane, if it would fly in space or inside the space capsule. And I had another one, but I can't think of what it was. Something to do with air and space. Well, anyway. Oh, well, thanks. Bye.
Well, believe it or not, you're asking a question that puzzled Albert Einstein back in 1915 when he finally came out with his general theory of relativity, more powerful than his earlier special theory of relativity. And that is, if you're in an elevator and someone snaps the cable, what is it like to be inside that elevator that's falling? Or if you're in a rocket ship, are the laws of physics different if you're traveling at different velocities? Well, this is the principle of relativity, that the laws of physics are the same no matter what velocity you are traveling at. So in other words, you ask us a question, if an astronaut lights a match on the space station, assuming it's safe to do so, then the question is, will the flame be just like normal? And the answer is yes, of course. However, there's weightlessness in outer space. And so the flame is not going to be shaped like a flame. It's going to be spherical, believe it or not. When was the last time you saw a spherical flame? But the laws of physics are the same in an object traveling at uniform velocity. And so flames, light bulbs, yeah, the laws of physics are the same no matter what velocity you are traveling at. Now, you may say to yourself, well, that can't be right, because if I get a flashlight, and if I shine a flashlight on the space station is moving at 18,000 miles per hour. Therefore, the light beam should get a boost. It should be traveling at the speed of light plus 18,000 miles per hour. Nope. The speed of light is always the same no matter where you go. How can that be? If I shine a flashlight forward, backward, left, right, upside down, forward, backwards, it always travels at the same velocity. How can that be? And the reason it is that way is because space and time are distorted so that the speed of light is the same. Now, you may say to yourself, well, that violates common sense. I mean, who could create a universe like that? Well, sorry about that. That's just the way the universe is. Get used to it. Okay, well, let's move right along. Let's take the next listener phone call.
Hi, Michio. This is Michael from Lansing, Michigan. I'm calling about the processing power of the universe, and if there is really such a thing. Maybe I'm thinking about this too much in terms of video games and computers, but I was wondering, how does everything stay generated all the time, everywhere within the universe? Thank you, Michio. Bye.
Well, you ask a question that philosophers sometimes ask, and physicists are now asking that question, and that is the universe itself a computer? Is it basically a computer that's doing trillions and trillions of calculations all the time? I mean, for example, if you throw a rock in the air, it obeys Newton's laws of motion, but who tells it? Is there a computer that tells the rock to obey Newton's laws of motion? Because we have simulators. simulators that can simulate a rock moving according to Newton's laws of motion, but that's a computer. The computer tells the simulated rock to move according to Newton's laws of motion, and then, of course, you get nice, beautiful parabolas. But the question is, who teaches or who tells the real rock to go in a parabola? At that point, you start to go crazy. You begin to think, well, is the universe itself a simulation? Are we living in an imaginary universe? I mean, look at the movie The Matrix. In the movie The Matrix, everything, like a falling rock, was due to a computer. A computer calculated the motion of a falling rock, and you had the illusion that the rock was falling. No, the rock wasn't falling at all. It's just a software program that was designed to create a rock to simulate a rock moving according to Newton's laws of motion. At that point, you start to go crazy, thinking about, well, how do you tell? How do you tell if the universe is a computer or is a simulation or not? Is it a falsifiable statement? Can you falsify a statement that the universe is a simulation? Now, look at it this way. Take a Hollywood movie on a CD and put it into your computer or your laptop or your TV set. Then all of a sudden on the screen, you see characters acting as if they were acting in the real world. You can imagine actors saying that, no, my universe is not a simulation. The universe is not a computer. I have free will. I can do anything I want because I am the master of my fate. But of course, you're listening to a movie in which the characters claim they have free will. They're acting of their own volition, that the universe is not a simulation. And so then the question is, how do you tell if everything is a simulation or not? Actually, I'm not quite sure. We physicists are debating this question even as we speak. There is something called a quantum computer. A quantum computer computes on individual atoms. One day it will replace silicon computers. That's why the CIA is very much interested in quantum computers. But then the question is the universe a quantum computer? Because the universe computes on atoms, because of course everything is made out of atoms. Well, like I said, at that point you start to go crazy thinking about, well, the movie The Matrix, was it really correct? We physicists are actually divided on this question. Okay, let's move right along to the next listener phone call.
Yes, my name is James Blaisdell, and I don't know the call number for the radio station that I'm calling from, and I would like to ask about cryogenics, if they're far enough advanced to be used for distance travel. Thank you.
Well, I think what you're getting at is cryonics, which is different from cryogenics. Cryogenics is the legitimate study of objects that are cooled down to very low temperatures. Cryonics is a rather dubious form of technology where you're frozen, and if you have a fatal disease and you're going to die of that disease, hopefully you can perhaps be revived at some point in the future. And at that point, we will have cured cancer and many other fatal diseases, and then you can live forever. In fact, you can actually do this on the web. If you look up cryonics, yes, they are commercial companies which say that they'll freeze your body in liquid nitrogen so that you could be traveling to a distant star at some point in the future, or just sitting in a laboratory waiting centuries into the future when there's a cure for many of these fatal diseases. Well, let me be very clear about this. In the history of science, we have not a single incidence of one man who's been frozen solid and then revived to tell about it. I repeat, there's not a single incidence of a person who's been frozen solid and then lived to tell about it after he's been revived. Now, you may say to yourself, what about animals? I mean, if you live near a farm, you know that when the lake freezes over, sometimes frogs and fish are frozen in the ice, and then when springtime comes along, the frog jumps out and the fish swim as if nothing had happened. Well, there's a secret behind this. It turns out that glucose, that is a form of sugar, is an antifreeze. Just like the antifreeze you put in your car in wintertime, it lowers the freezing point of water so that your car can still function even when it's ice cold outside. In the same way, the bodily fluids of these animals are still liquid, even if they're frozen solid in a block of ice. Now, why can't you do that for interstellar space travel? Or why can't you do that to live forever? Well, there's a problem. The amount of antifreeze necessary to do this in your body will kill you. In fact, some people say, well, why can't we use other antifreezes? Well, they've been tried on animals. It turns out that the results are usually fatal. The results are that large animals simply cannot be frozen using some of the antifreezes that you find in a chemical laboratory. Now, let me be very, very clear about this. That doesn't mean that at some point in the future, somebody may figure out how to do it. That's always possible. So maybe, yes, maybe somebody who's frozen solid might be able to be thawed out at some point in the future. But at the present time, we don't know how to do it. At the present time, it's an untested technology. And at the present time, nobody has ever been thought out this way. Okay, moving right along, let's take the next listener phone call.
I was wondering what the frequency of the gravitational wave recently discovered with the gravitation detector equipment. And this is Constance from Warren, Michigan. Thank you.
Okay, well, yes, a few months ago, it hit the headlines, not just once, but twice. Scientists have actually detected vibrations from colliding black holes in outer space. Let me begin by breaking it down. Back in 1915, Einstein proposed a theory of gravity that said that gravity is actually due to the fact that space-time is like a fabric that can stretch. And if you are then moving along the fabric, then your path is bent sideways or whatever, just like what gravity does. And just like the surface of a pond now, if you were to throw a rock into a pond, you get ripples forming on the surface of the pond. And then Einstein said, well, gravity must be like that. If I have a tremendous disturbance, then shock waves should emanate from the impact, and we should be able to observe that with our instruments. However, he did a quick calculation, and he quickly realized that in his lifetime, he would not be able to detect these gravity waves. So this went on for 100 years, from 1916 to 2016. For 100 years, scientists have tried to look for gravity waves. And they did it by building a gigantic machine called LIGO, two of them, one in Washington State and one in Louisiana. It's basically two laser beams that form a joint. It looks like an L. When these two laser beams collide, they form an interference pattern, just like the interference pattern you get on the surface of your bathtub if you make waves on the surface of your bathtub. Well, if there is a colliding black hole in outer space, it creates waves. These waves then hit the laser beams, jiggle the laser beams, and then our instruments are sensitive enough to be able to detect the fact that they've picked up the vibrations. Then you can take these vibrations, run it through an audio amplifier to get sound waves coming out of it. Now, the media call this the music of the spheres. That is music from black holes. Actually, it's not anything of the sort. But, if you stretch your imagination a bit, what we're talking about is gravity waves from space-time itself jiggling a diaphragm, and the diaphragm then jiggles air waves, giving you sound. And if you go to nasa.gov, you can actually find the link where you can listen to it. You can actually listen to some of the vibrations. Now, the frequency of these vibrations is pretty low because you're talking about sound frequencies, and it really has not much to do with the real physics of what is happening. The real physics of what is happening is when I have what is called a spin 2 wave coming at you that can then be broken down using electromagnetic sensors and laser beams. But it's kind of cute. It's kind of cute the fact that you can then take this electromagnetic wave, run it through a sound amplifier, and hear it. But you're not really hearing the black hole, as the media said. Okay, well, let's now take the next listener phone call.
Hey, Dr. Kaku.
My name is Wade Anderson. I'm calling from Rainsville, Alabama. And I was just wondering is it not possible that darkness is faster than light? Because I've seen programs that show black holes in space that light cannot escape. Thank you.
Well, the short answer is no. It turns out that darkness is nothing but the absence of light, and therefore light travels at the speed of light, obviously. So the absence of light, that is a shadow would also emanate and move at the speed of light. Now, black holes, as you pointed out, light cannot escape from a black hole. Light simply orbits around a black hole. But if you are in the frame, that is, if you're in a rocket ship traveling along the light beam, it would also travel at the speed of light. And so any way you cut it, you cannot break the light barrier this way. Darkness does not travel faster than the speed of light. Darkness is nothing but light itself. But here's a question that I asked myself when I was a kid. If you get a flashlight and zip it across the heavens, from one side of the heavens, one horizon, to the other horizon, and you were to go far enough out there in outer space, didn't that light beam go faster than the speed of light? Because you went from one side of the universe to the other side of the universe at a velocity much faster than the speed of light. And the answer to that is actually yes. However, you cannot send net information this way. Yes, it's true that if you get a flashlight and zip it across the night sky, then the image will actually travel faster than the speed of light. But you cannot send usable information that way. Here's another example. Let's take a pair of scissors and close the scissors, and then calculate the speed at which the joints of the two blades converge. If you go far enough into outer space, assuming these scissors are huge and very lengthy, then at a certain point, the joining point joins faster than the speed of light, because, of course, the scissors are millions of miles long, and you close them very rapidly. If the blades are long enough, then the joint will also close faster than the speed of light. But again, it's useless information. You cannot send Morse code this way. You cannot send usable information. So can some things travel faster than light? The answer is yes. Images. Images will go faster than light, like zipping a flashlight across the night sky. But it's fake in the sense you cannot send Morse code this way. You cannot send usable information to the nearby stars faster than light. Well, let's take the next listener phone call.
Hey, it's 8:20 a.m. in Tampa, Florida. The theory of relativity was first published by the Frenchman Henri Poincaré before Einstein later plagiarized it. Then this general theory of relativity is not a general theory of relativity at all. It's just a theory of gravity. Einstein had no business calling it a general theory of relativity, and it was first published by David Hilbert, the German David Hilbert. So why is his name in any of the physics books? He didn't do any of these things if you look closely at it. Thank you.
Well, you ask a very interesting question, and I once wrote a biography of Albert Einstein called Einstein's Cosmos, where I actually went through each and every one of the claims that you mentioned. Well, first of all, as most historians know, and as Einstein himself said on a number of occasions, that when he wrote down the theory of relativity in 1905, well, yeah, there were other people that were very close to getting it, but they didn't have the full Lorentz transformation, and they misinterpreted the data all incorrectly. First of all, if you shot a light beam in the forward direction and sideways, you would expect the velocity of light to change depending upon the direction of the light beam. If I have a flashlight and I shine it forward, backward, up, down, left, and right, you would expect the speed of light to be different depending upon the direction that you sent it. But no, it comes out the same every single time. And so, since the Earth moves in space, people said that the Earth must be moving in an ether wind, and the ether wind makes the yardstick contract. And therefore, there were all these papers trying to create a mechanical contraction of meter sticks in order to get the Michelson-Morley experiments to come out right. Well, Here comes Einstein and says, no, 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 you got it all wrong. It's space itself. It's space that is contracting. That means that everything in space, not just meter sticks, but people, brains, bodies, everything contracts along that same direction. So in other words, he was proposing a general principle for all of reality, not simply an electromechanical effect to explain the fact that meter sticks were coming out wrong. Now, yeah, Poincaré was very close. Other people were close. Lawrence Fitzgerald, yeah, they were close. And Henri Poincaré, the great mathematician, was also very close. But, again, they missed it. They didn't realize that these effects were effects that affected the speed of time and space itself. They all missed it. Einstein was saying that even clocks, everything, not just meter sticks that you measure in the Michelson-Morley experiment, but reality itself was slowing down. That was mind-boggling, and only Einstein got it right. Second of all, Einstein then came out with the theory of gravity. It's called general theory because it's more general than a theory of light. It's a theory of gravity because back then they didn't know about the nuclear force. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, where we last left off, a listener called in and said, wait a minute, maybe Einstein has to share the credit, or maybe he even stole some ideas from David Hilbert, a famous German mathematician who published some of these ideas. Well, I looked into the history of that charge. It turns out that from 1905 to 1915, Einstein was struggling for a general theory of relativity, a theory not just of light, but of gravity as well. Because back then, that's all they knew about. They didn't know about any nuclear force. They thought that that was it, light and gravity. That's what made the universe tick. Well, David Hilbert, being a mathematician, comes out with a list of unsolved questions in mathematics. He challenged the world of mathematics to solve these unsolved problems. And of course, the world's greatest minds tried to solve these problems. One of the problems that David Hilbert wrote about was to mathematically put down all the laws of nature, all of them, all the laws of physics into a single framework. Well, he heard that Einstein was working on this. And so he invited Albert Einstein to give 3 long lectures at his university about his unfinished general theory of relativity. So then Einstein elaborately laid out this enormous mathematical structure using tensor calculus, the Ricci tensor, using the most advanced forms of mathematics known at that time as an attempt to create the unified field theory. Well, Hilbert, being a mathematician, realized that there was one thing missing in this elaborate mathematical framework, and that is a series of identities called the Bianchi identities. And Hilbert, being a mathematician, said, well, look, you, Einstein, have laid out this tremendous apparatus, this huge mathematical foundation, but you miss one last step, and that is the Bianchi identities. Well, Hilbert, being a mathematician, completed it and published it without giving Einstein credit. Well, this was scandalous, absolutely scandalous. Here was Einstein, who had given a series of talks. Many people had heard his talks, laying out the mathematical foundation of general relativity. And he, in turn, also later got the Bianchi identities, and he finished it. So he published his theory in November of 1915, shortly after David Hilbert also published his theory, which, of course, was the same theory, because he copied it from Albert Einstein. Well, Einstein was PO'd, to say the least. He even wrote a letter to Hilbert a few months later, saying that at first I was irritated, but now I've gotten over it. So in other words, Hilbert was a great mathematician. He did complete the last mathematical step leading to what is called today the Einstein-Hilbert equation. And so in honor of both individuals, we call it the Einstein-Hilbert action. All textbooks will say that. But everybody knows who really got it first. Everybody knows who wrote the foundation, who wrote the mathematics, who wrote the entire framework, but he just missed the last step, which was the Bianchi identities. And in fact, it's now a stain on Hilbert's reputation that he actually tried to steal an idea from Albert Einstein in order to complete one of his unfinished problems in mathematics. But like I said, we physicists, we have completed the dots. In fact, we even now have the notebooks of Albert Einstein going year by year. In fact, in 1912, 3 years before, he actually got the correct equation, but he made a mistake, a mathematical mistake, and crossed out that equation. But he actually had the general theory actually back in 1912, 3 years before David Hilbert. And so the lesson is, yes, we're all human. Even the greatest mathematician of his time, David Hilbert, could try to swipe a theory from the greatest physicist of his time, Albert Einstein. Okay, well, let's move right along to the next listener phone call.
Hi, my name's Eugene Pate, and I just listened to your radio show about Stephen Hawking's idea of sending a postage-sized spacecraft to another planet. Well, the whole idea of building the lasers and stuff seems sort of prohibitive. What's wrong with the idea of building a small miniature rocket ship with a small amount of rocket fuel that you could take aboard the space shuttle, much like a model rocket with the same postage-sized technology on it, and since you've got something already in space and doesn't have to escape the atmosphere, you can shoot this towards another planet and have a little fuel left for guidance along the way. But once you put an object in motion in space and attain a certain speed, there's nothing to slow it down. So you could just take a rocket up on the space shuttle with your postage stamp technology and launch it in space.
Okay, well, I have 10 seconds to answer that question, and that is, your idea is ingenious, but it's not going to work because you need 800 megawatts. That's the power of 800 nuclear power plants, and you can't put that on the International Space Station. It's simply prohibitively expensive. Okay, well, once again, you've been listening to Science Fantastic with Professor Michio Kaku.